Hi, myself Dr. Kamal Kumar, Department of Physics, New College, Moradabad, which is affiliated to Guru Jambheshwar University, Moradabad. I would like to thank for the refresher course on recent trends in artificial intelligence to the MMTC of Deen Dayal Upadhyay University, Gorakhpur. The topic of my presentation is Heavy Ion Induced Nuclear Reaction, BI-assisted future, transition from manual accelerator workflows and statistical models to intelligent hybrid physical systems. The four pillars of the nuclear inquiry: theoretical mechanics, physical experimentation, computational modeling, and the AI upgrade. The trajectory of a projectile depends on its energy, hence the impact parameter is also important to understand these reaction dynamics. On the basis of the impact parameter, the small impact parameter is associated to the complete fusion reaction dynamics. For grazing the incomplete fusion, deep elastic collision takes place. However, in case of the peripheral B, the elastic scattering and direct reactions occur. For the distance B, the Rutherford scattering comes into the picture. When the two entities, projectile and target, comes in close, then optical model potential comes in the view, which is also consists of two parts: elastic scattering and the reaction. The real part is associated to the elastic scattering or rather four kind of scattering, while the imaging part consists of due to the various reaction processes depending on the impact factor B. The projectile dynamics structural clustering detects pathways for alpha clustered projectiles. The 16 oxygen and 12 carbon projectiles like the near Coulomb barrier energies dominating trigger complete fusion processes, while increasing energies incomplete fusion becomes essential pre-equilibrium emission may occur before equilibrium is established. However, in case of the non-alpha cluster projectiles like 18 oxygen, 14 nitrogen, the behavioral shift prone to divergent pathways due to the lack of distinct alpha structures or substructure. Transfer reactions actively observed alongside standard fusion scattering processes. In case of complete fusion, a projectile fuses with the target nucleus. However, in case of the incomplete fusion, projectile breaks before the close collision to the target, and the remaining part goes in the forward direction without any deflection. The accelerator is used for these reactions, which is situated in the valley. The interchangeable ion source and injector magnet, initial beam generation and injection into the primary stack. High voltage terminal and charge stripper housed inside a sulfur hexafluoride tank, stripping electron to accelerate positive ion. Analyzer magnet is used to to direct the beam towards the target area. The physical life cycle of heavy ion experiment. The target lab is used to prepare target and catcher files. The stack is irradiated in a general purpose scattering chamber. The beam is directed through degrader and target samples into the Faraday cup. The induced activities are catched by using the multi-detector and capturing the resulting complex emission. This is a typical example of the spectrum which is observed at energy 100 near about 100 MeV for a 16 oxygen 165 volume reaction. The various peaks are uh, characteristic gamma rays of various evaporation residues which are populated in this reaction. A particular evaporation residue can be identified on the basis of its characteristic gamma ray and half-life by using decay curve analysis. Various code can be used for the theoretical predictions of these reactions. However, phase 4 is generally used by us. This is a typical example of the calibration of theoretical data, the theoretical model while using the experimental data. Various level density parameters change to get the best input parameters. The current bottleneck in nuclear research: observation, hardware complexity, accelerator patterns require intensive annual human optimization, beam tuning, and physical monitoring. Observation 2. Data extraction fixture. Friction isolating specific decay signature from highly congested gamma ray spectrum is labor intensive, computationally slow, and prone to human error. Observation 3. Rigid simulation. Statistical decay code rely on fixed physical parameters and fundamentally struggle to dynamically adapt to anomalous cross-section data. The artificial intelligence upgrade, rapid evolution, machine learning algorithm deploy pattern recognition to instantly evaluate nuclear data, isolating gamma ray signatures from background noise magnitude faster than manual extraction, predict cross-section, deep learning modeling trained on legacy database to predict fusion transfer reaction cross-section with higher fidelity and traditional statistical code, beam optimization, AI-driven control system interface directly with accelerator hardware to autonomously optimize beam tuning targets stabilizing operational real-time. The workflow evaluation, traditional versus AI associated diagnostic, the legislate says manual parameter tuning is rigid statistical code, while in smart lab hybrid physics AI simulation with continuous self-adjusting weights. In legacy lab, human accelerator tuning and reactive beam stabilization, while in the smart lab, autonomous control system and real-time smart hardware integration. In the legacy lab, analysis, manual decay, curve fitting, and gamma ray spectrum isolation. While in the smart lab, machine learning assisted signal extraction and automatic classification. In the legacy lab, validation, reactive constraints, physical experiments must be designed specifically to fix model error. While in the smart lab, protective discovery, AI autonomous designs experiments to probe the stability and uncertainty. The future perspective, the hybrid physics AI feedback loop. The future of heavy ion reaction is not about replacing traditional physics but enhancing it. Physical model constrain the AI while AI optimizes the physics. The theoretical parameters, level densities, optical potential. In case of the physical experiment, electron irradiation, multi-detector data, the machine learning injection, empirical data feeds directly into neural networks, autonomous model meant AI dynamically defines theoretical physical parameters. A new era of precision nuclear dynamics, heavy ion induced reaction provide a critical window into the world nucleons governed by their delicate impact parameters and complex projectile clustering, while robust experimental setup and statistical code have led to foundation the fundamentally constrained by human analysis speed and digit modeling algorithms. The integration of machine learning into nuclear data evolution and accelerator control is no longer optional. It is definitive next step towards the realization the smart nuclear laboratory. These are some suggested references for this study. Thank you.